Okay, I want to do a video on a part of discrete math which I often cover in the discrete math class, but it's not in the book at all. I'm not sure yet whether I'm going to have you do anything with this. I don't know if I'm going to have exercises or not, but I want to at least cover it. And then if I decide to add something later on, I'll give you fair warning and enough documentation and so on to work with it. Otherwise, I just want to at least expose you to this so you've seen it. It's really helpful stuff in some areas of computer science, of engineering, other things like that. There's not a lot that you use this in high-powered ways with, but there's a lot of places where you'll run into this terminology the rest of your math life, especially if you're in some other areas as well, like engineering or computers. They'll often use the phrases that I'm about to talk to you with, and that'll be important. By the way, part of what I'm going to talk about is functions, and that's something you're certainly familiar with. So what I want to talk about is the idea of a relation. And this is very much a part of set theory, or at least it flows from set theory. We're going to talk about relations. So I'm going to give you a ton of definitions here. I don't think anything here by itself is tricky, but it's a lot easier for me because I know all the definitions. It may be overwhelming at a certain point after you've got like 17 definitions on the board. It may be hard to remember what any of these mean. So I'm just going to cover them anyway, do the best I can to clarify it, and then you can always go back if you want to look in more detail. So first of all, what is a relation? Well, to talk about what a relation is, we need to talk about the Cartesian product of two sets. If you have a set A, let's suppose it's 1, 2, 3, and a set B, let's suppose it's A, B, C, D. No reason sets have to have numbers. They could have other things. The Cartesian product, well, you know what we can do. You know how to calculate A union B, A intersect B, and so on. The Cartesian product is written A cross B, A x B. Usually that's pronounced cross, or sometimes it is. And it is the set that contains all the ordered pairs you can form from the elements. So in other words, it is the following set. It has the pair 1A, the pair 1B, 1C, 1D, 2A, 2B, 2C, 2D, 3A, 3B, 3C, and 3D. Okay. So if we have 3 elements in the first set, 4 elements in the second set, we end up with 12 elements here. Now, one thing I want you to notice is that this is a strange set. You don't end up with single elements over here. You end up with ordered pairs over here. So the elements of the set here are pairs of things, 1A, 1B, 1C. The second thing is these are ordered pairs. So if we had, say, a 1 in both sets, we could have both 1, 2 here and 2, 1 here, or something, if we had 1 and 2 in both sets. So it matters here whether I say 1A or A1. 1A is in the set, A1 is not, because there's not an A in the first thing and a B in the second one. One way to think about this is I'm drawing 2 sets of axes. And along one set of axes is 1, 2, 3. And along the other set is A, B, C, D. And I'm looking at all the points that gives me. 1A, 1B, 1A, 2A, 3A, 1B, 2B, 3B, and so on. Okay. This is called the Cartesian product, and it's useful for a lot of different things. But one of the things it's useful for is in defining relations. Okay, so let me erase all this, and I will tell you the definition of a relation. Okay, here we go. A relation R from A to B, A and B are sets, is a subset of A cross B. And then similarly, a relation R, on a set S is a subset of S crossed with itself. All right, so let me give some very specific examples, and this won't make any sense yet. I mean, it'll make sense, but you'll be like, why are we even looking at this? And then I'll show you what we're really talking about. So let's suppose that A is ABC, and B is ABD. In that case, A cross B is all the different combinations we have of A followed by B. So it's AA, AB, AD, and then BA, BB, BD, and then CA, CB, CD. It's that whole set of things. When we say that R is a relation, we mean is R is some subset of these things. So R, for example, might be the following subset: AA, BD, and CA. Okay. Any subset of these things. So in other words, a relation is just any combination of pairs where the first part of the pair comes from A and the second part of the pair comes from B. There's usually a convenient way to write this for finite small sets. I'll draw A over here with its elements, A, B, C. And I'll draw B over here with its elements, A, B, D. And I'll put a line wherever one of the elements on the left is paired with one of the elements on the right. A and A are paired, so A is paired with A. B and D are paired, so B is paired with D. And C and A are paired, so C is paired with A. And the lines here represent the relation. So you can see what's going on here is that a relation means that two elements are related to each other. That a relation is actually, let me say it more carefully, that two elements are related means there's some sort of connection between them, and the relation is the set of all the connections that there are. So for example, A might be the set of all the people in Sterling, and B might be the set of all the people in Rock Falls. And then you could say that the relation we're interested in is the relation of people being related to each other. And you draw a line between everybody in Sterling and whoever they were related to. Actually, so let me not use related because that's the same word. Let me say this differently. Let's let the first set be the people in Sterling. Let's let the second set be the people in Rock Falls. And let's suppose that we want to look at whether the people in Sterling actually know the people in Rock Falls. And so if there's a person in Sterling who knows a person in Rock Falls, we'll draw a line between them. This person knows this person, and this person, and this person. And this person knows that person, and this person, and this person, and so on. So you draw all the lines. That entire network of lines is the relation. In other words, it's the pairs that we're interested in. So a Cartesian Cartesian product is all the pairs there are, and a relation is a certain subset of pairs that you're interested in, and that makes it a relation. Now, relations are used for a ton of different things. They're like functions, except functions are a specific type of relation. It's any time you have any connection, but you're formalizing any connection between one set and another. Now, a relation R on a set S means that the two sets are the same. So this would be if you looked at everybody in Sterling and everybody in Sterling, and then asked who knows who, and you drew lines between every two people who knew each other. That would be the relation, and it would be using the same set on both the beginning and the starting and receiving ends of the pairs. All right, so let me add one more piece of notation, and then I'll show you how we use this, and it'll make hopefully even more sense. The notation that we'll use is we'll put R, if something's in R, we'll use R as a symbol and put it in between two elements. So let me show you what I mean. The technical definition is this. If AB is in R, we will write, ARB. Now this looks strange, but what I mean is if A and B are related, using this relation, we'll write ARB. Now, let me show you how this works by using several examples. One of the most important examples of a relation is less than. Less than is a relation on numbers. So for example, we might have less than defined on natural numbers, 1, 2, 3, 4, 5, etc. And when we write 3 is less than 5, we mean that 3 and 5 are paired in the set defined by the relation, the set which is the relation. And you would call the set, I guess, less than, which is a strange name for a set. But you're saying, here's this set of less than pairs. 3, 5 is in that set. We'll just write it by saying 3 is less than 5. You would actually call the set less than here, but nobody does that. They write it this way. If you have equals, you're saying that every two things are related only to them. Things are only related to themselves. And so the relation is the set of pairs that are A, B, B, C, C, and so on. And you'd say something like x equals 3 because x and 3 are related. So basically you put relation terms, the whatever symbols you use for the relation, you put in between the two elements. Okay. I don't know if that made a lot of sense, but hopefully it will as we continue to do more examples. So that's the terminology. Let's see. Now, where are we going with this? There are 3 important types of relations. So let me erase this and tell you about the 3 important types of relations, and then we're going to spend some time with each one. This is where the theory starts to make sense. By the way, graphs are closely related to relations, no pun intended. A graph is just like a relation, except that it's not ordered. With a graph, you can have an edge going in both directions. So if you put arrows on the graph and make it a directed graph, it's exactly the same as it's just a picture of a relation. So here's the definition. Remember, relation is a subset of A cross B, or a relation on a particular set is a subset of the set with itself. Remember that something being related to itself is written this way. Okay, let me prime my marker a little bit better. Okay, there are 3 types of important relations, or 3 important types of relations that we need to talk about. The first one is functions. Okay, so you already know all about functions, but we're going to think about functions here as just a special type of a relation. So here's my picture. Here's a relation from A to B, A, B, C over here, D, E, F, G over here. I have a relation like this. Okay. In this particular relation, A relates to D and E, B relates to E only, C relates to E and F. And looking on the other side, so over here's A, over here's B. Looking on the other side, D has A related to it, E has A, B, and C all related to it, G has only C related to it, F doesn't have anything related to it. All right, this is not a function. And the reason it's not a function is because the rule for a function is anything on the left can only be related to one thing, has to be related to exactly one thing on the right. So a function is, so let's put it this way. A relation from A to B, a relation R from A to B is a function. This is a definition. If every A in A is related to exactly one thing in B. I'm sure you know this. It's the way functions always work. So the idea is this is not a function because if you give me A, there's 2 things it's related to. But if I eliminated one of these things from A, it would now be a function. If A only went to D, it would be fine. And if B only went to E, well, it wouldn't be a function yet until I fix B as well, and C. And if C only went to E, this would now be a function. A goes to E, A goes only to one thing, B goes only to one thing, C goes only to one thing. That's a function. So the key idea behind a function is you think of the first set as your input, the second set as your output, and it needs to be unambiguous. That is, if I tell you the input, you should be able to tell me exactly what corresponds to it on the other side. While A was related to two different things, it wasn't ambiguous. I didn't know whether it was related to one or both, and which one to choose. But if it's a function, if you give me the first thing, I always know what it leads to on the second side. Okay. Notice it doesn't necessarily work the other way around. If you give me E, I don't know where it came from. Could have come from either B or C. But that doesn't stop it from being a function. It's still a function as long as everything on the left has one unambiguous related thing on the right, and that's exactly how many it has, just exactly one. There's always related to something, never related to two things. So you know that that's how it works. We use that in algebra and everything else. But it's a special kind of a relation. Okay. That's why when I was talking about MP and P, I talked about the non-deterministic polynomial non-deterministic Turing machine, and I said instead of functions in that table, it's actually a relation. And that's what I meant was it doesn't have this one-to-one property, or this property right here. Okay. Once you look at functions, there's, let's see. So now two other bits of terminology. When you have a function from A to B like this, there's three things to think about. One is A, and that's known as the domain. Now, there's another set of terms you've heard, but I want to be more careful than it's often done. Usually, the range here is everything that A is related to. So the range is D and E. And the codomain is B. So the range, the domain is everything you have the relation starting from. The codomain is everything you had the potential of the relation, everything you have the relation ending in. It's all the potential ending parts of the pair. But the range is the actual ending parts of the pair. Most people in most classes don't distinguish between range and codomain. They just talk about the range. But technically speaking, the codomain is the set you could have had, and the range is the set you do have. So if I was looking, for example, at the square root function, well, let's not do that. If I was looking at the squared function in a regular Cartesian plane, the domain is the real numbers because it's the entire set of x values all the way from one end to the other. The range is only the non-negative real numbers because you never get negatives. But the codomain is still the entire set of real numbers. You're just not using them all. Okay. Most of the time, people don't care what you're using if you don't actually end up having it as an answer. So, domain, codomain, and range. Now, once you talk about functions, there are three more terms you can talk about. Function can be onto, or one-to-one, or it can be a one-to-one correspondence. There's a difference between being one-to-one and being a one-to-one correspondence. There are more technical terms for these. Onto is sometimes called a surjection, or it's called surjective. If it's one-to-one, it's called injective. And if it's a one-to-one correspondence, it's called bijective. Okay. Here's the idea there. If it's onto, it means that the codomain is the same as the range. In other words, an onto function, I was going to say relation, but that'd be true too, but functions are what we're talking about in this case. An onto function is one in which every single thing on the right is hit by something. Let's suppose we have 4 on the left, and they are sitting like this. I'm not going to put numbers on them. This is onto because every single thing in B is related to something. So onto specifically a function from A to B is onto if every B in B is related to something in A. All that means is that you have to have a line landing everywhere over here. If you have an extra one here, it's not onto. In other words, if the range is equal to the codomain, it's onto. If it's different, it's not onto. It's into, but not onto. One-to-one means that everything on the right-hand side has at most one thing related to it. So a function from A to B is 1 to 1 if every element in B, every B in B, is related to at most one element of A. So this is not 1 to 1 because there's something that has two lines coming into it. If we took one of those out, well, we still have a problem here. Let me rewrite it. This is 1 to 1 because not only does each of these only have one thing on it, each of these only has one thing on it. Now this one right here doesn't have anything on it. That doesn't violate 1 to 1-ness as long as there's never more than one. So onto says you have at least one everywhere over here, and 1 to 1 says you have at most one everywhere over here. A 1 to 1 correspondence is really simple. It just means 1 to 1 and onto. So if something's 1 to 1 and onto, every element in B has exactly one element in A that's related to it. Nothing over here has more, nothing over here has less. Now, if you think about it with 1 to 1 correspondences, they can only happen where the sets are the same size for finite sets. Actually, for infinite sets too. They can only happen where the sets are the same size, because if you have too many over here, one of them has to be left out and it can't be onto. And if you don't have enough over here, one of them has to be duplicated and it can't be 1 to 1. But if you have the exact same number, it can be 1 to 1. Now it doesn't have to be. Here's another relation between two things which both have 4 elements. Oops, that's not a function, sorry. Two things which both have 4 elements. And it is a function because each of these only has one thing on it. It's not 1 to 1 because this one has 2, and it's not onto because that one doesn't have any. So you can have something that's neither 1 to 1 nor onto, and it still has the same number of elements. But if it's 1 to 1 and onto, it does have to have the same number of elements. So that's what a 1 to 1 correspondence is about. The 1 to 1 correspondences are sort of unique in that they're invertible. What that means is if you take a 1 to 1 correspondence and run it backwards, it's still a function. It's still a function because on the one hand, because it's 1 to 1, you know that you only have one thing coming from each one. And since it's onto, you know that it's a function defined for the entire set and not just for a portion of it. So 1 to 1 and correspondences are invertible functions. I did that pretty quickly, but I'm assuming you know most of that. You just haven't thought of it in terms of relations before. The second kind of relation that's really important to know about is called an equivalence relation. This is very different. For this one, don't think about functions. Think about operators like equals. Equivalence relations are things that are properties of sets that are properties of things that tell you whether two elements are equal or equivalent in some way. That's why it's called an equivalence relation. So equals is an equivalence relation. Equivalent in terms of sets having the same size is an equivalence relation. Congruent triangles in geometry is an equivalence relation. Things both being even or odd is an equivalence relation, the parity of something. Whether something's divisible by something else is whether things are divisible by 2, for example, which is even or odd, is an equivalence relation. I shouldn't have erased that, but I will anyway. So an equivalence relation is used for things that are the same in some way. So in math, it's things that have the same size or the same sign or the same divisibility by 2. Or they're the triangles, if you're looking at congruent triangles, which you probably haven't gotten to yet, the congruent triangles are not in the same position necessarily, but they're the same shape and size. Similar triangles are different sizes, but they're still the same shape. Those are all equivalence relations. You can think of equivalence relations in everyday language too. If two people or two things are equivalent in some way, it's probably an equivalence relation. So if you looked at people having the same age, or having the same name, or being in the same class, or actually that one, it's not an equivalence relation. I'll come back and talk about it later. But those things are known as equivalence relations. So let's talk about what makes something an equivalence relation. To be an equivalence relation, you need 3 properties. A relation R on S is an equivalence relation if it is reflexive and symmetric and transitive. Has to have those three properties. And these are important properties to understand. Okay, so reflexive means this. A relation R on S is reflexive if for every element x in S, x is related to x. So being reflexive means that everything has to be related to itself. Is having the same first name or an equivalence relation? Well, that's too early. Is having the first name reflexive? Well, does every person have the same first name as themselves? Yes. Then it's an equivalence relation if it's for people. Does having the same sign, positive, negative, or zero, positive or negative or zero, is that equivalence relation? Well, does everything have the same sign as itself? Then it's an equivalence relation. If something's always related to itself, no matter what it is, then your relation, I'm sorry, it's not, it doesn't make an equivalence relation, it makes it reflexive. If something's always related to itself, no matter what it is, then your relation is a reflexive relation because every individual thing is related to itself. In terms of pictures, this means if I drew a single set and then I had arrows from thing to thing within the set, being a reflexive relation means that every single thing would have a loop relating itself to itself. Okay. The second thing is symmetric. I'll skip the preamble. A relation R and S is symmetric if for every x and y in S, if x is related to y, then y is related to x. What this means is a symmetric relation goes both ways all the time. So if one thing is related to the other thing is related to it. So if A is equal to B, then B is equal to A. If I have the first name as you, then you have the first name as me. Now, symmetric relations, not all relations are symmetric. Less than is not a symmetric relation. If 5 is less than 6, that doesn't mean that 6 is less than 5. So symmetry has to do with commutativity. If this relation gives you a kind of commutative relationship, then it's definitely symmetric. Also, not everything has to be related to everything. This doesn't mean that everything's related to each other. So marriage is a symmetric relationship because if you look on people, if you have a set of people and you look at the relationship of marriage, then if A is married to B, B is also married to A. But it doesn't mean A is married to B. Not everybody's married to everybody. But if you were married, you'd be married both directions. So relations that are symmetric are things where it runs both directions. One way, again, to say what I said before is graphs are actually simply equivalent to symmetric relations. Okay, the third thing is transitive. A relation R and set S is transitive if for every A, B, and C in S, or X, Y, Z in S. Let's use X, Y, Z. Doesn't matter. If X is related to Y and Y is related to Z, then X is related to Z. Transitive relations are relations that chain. Think less than. If 5 is less than 6 and 6 is less than 7, then you know for sure that 5 is less than 7. If I'm taller than you and you're taller than him, then I'm taller than him. So taller than is a transitive relation. So a lot of things are transitive, but only if they chain that way. Everybody complains every year in sports that beating somebody in a sport is not transitive. Team A can beat Team B, and then Team B can beat Team C, and then Team C can turn around and beat Team A. And it confuses everybody, like with football, because they never know who should win who should get invited to the bowl games and so on. People always have arguments about this. Well, we beat them and they beat you, so we're better than you. No, not necessarily, because beating somebody in a game is not usually transitive. But transitive things chain. If one thing is related to a second and the second is related to the third, the first is related to the third. Now, less than and taller than are not equivalence relations because nobody's taller than himself and it's not symmetric. But when something is transitive along with being symmetric and reflexive, then it's an equivalence relation. So think about some common equivalence relations. Having the same sign. everything has the, meaning positive or negative, everything has the same sign as itself. If x has the same sign as y, then y also has the same sign as x. And if x and y have the same sign and y and z have the same sign, then x and z have the same sign. Think about having the same name. If I have the same first name as you, well, I have the same first name as myself, it's reflexive. If I have the same first name as you, then you have the same first name as me, it's symmetric. If I have the same first name as you and you have the same first name as the third person, then I must have the same first name as that person, so it's transitive. So anything you have something that's all three of those, it's an equivalence relation. And the idea here is things that apply to equals and other things like equals apply to basically all the different equivalence operators no matter what you pick. So any relation that's equivalent, that's an equivalence relation, you now can say a lot of other things about it. So a lot of times people go to great trouble to try to find something and then show that it's an equivalence relation. If you can show that it is, then you get all this other stuff that we're not going to cover as along for the ride just because you know those two things are equivalent. I said being in the same class is not an equivalence relation. If I'm in the same class as you, I'm always in the same, if I'm I mean like a school class. If I am in a class at all, I'm in the same class as myself. That might already not be an equivalence relation because if the people we're looking at, if some of them aren't taking classes at all, then they're not related to themselves. But suppose you're only looking at people who are going to class. Then it would be reflexive because everybody would be the same class as themselves. And if I'm in the same class as you, you'll be in the same class as me. But it's not necessarily transitive because I may be in one class with you and you may be in a different class with somebody else and I may not be in a class with that person at all. So that's not an equivalence relation. But some things, many things are. The last thing I'll mention is orders. And this won't take very long. It's related to what we just did with equivalence relation. The third special type of thing is what are known as partial orders. And then total orders are a subset of partial orders. Partial means partial or total. And then total orders are a special class of those. Okay. A partial order is something that is a reflexive, just like equivalence classes. And transitive, just like equivalence classes. But instead of being symmetric, it's anti-symmetric. So anti-symmetric means this. It means if x is related to y and y is related to x, then x and y have to be equal. This says not only is it not symmetric, no two objects, it never works out to go both ways for any two pairs, any two things in a pair unless they're the same thing. An example of anti-symmetric is less than. Or let's do this more carefully. The example of anti-symmetric is less than or equal to. If number x is less than or equal to y, and number y is also less than or equal to x, then they have to be equal. That's the only possibility. Subset. If A is a subset of B, and B is a subset of A also, then they've got to be the same set. So anything that looks like a less than or equal is anti-symmetric. Now, if something is in addition, reflexive and transitive, then it forms a partial order. So the two most important partial orders are less than or equal and subset. And let me draw this a little lower. I'll give you these examples and we'll call it a day. Less than or equal and subset. Okay. So what I want to point out is when you have a partial order, it forms a hierarchy. So if we take the numbers, just the natural numbers, n, they form a hierarchy where 1 is less than 2, which is less than 3, which is less than 4, etc. And what goes on is every number is less than or equal to itself. They're never less than or equal in both directions, unless they're equal. But it is transitive. If 1's less than 2, which is less than 3, 1 is less than 3. So you can draw partial orders in like a diagram like this with a hierarchy. Think of this as people in a business. You know, the president is in charge of, the vice president is in charge of, you know, an assistant somewhere, which is in charge of, you know, whoever else. And there's a clear line of command. And that clear line of command happens because of the transitivity and this anti-symmetry. And the reflexivity is just thrown in there as well. Now, subsets are a little different. Suppose we look at the set ABC, and then we consider all possible subsets of that. Okay, ABC is at the top. The biggest subset of ABC is just the set itself, ABC. But subsets of that include AB and AC and BC, or just A, or just B, or just C, or the null set. want to do this properly. A and B are both subsets of AB. A and C are both subsets of C, and B and C are both. Here, B is a subset of these two. I did this badly, but what I've drawn here is this is a subset of all of these. These are a subset of the two that I've drawn the line above them to, and then these are a subset of all those, and it's transitive. So we have a hierarchy here where this is sort of the one at the top, and then below it are the next smaller, the next bigger the biggest subsets we can get that are smaller than it. Below that are just the singleton subsets. Below that is the empty subset, and there's a hierarchy. Every single one of these is a subset of itself, so it's reflexive. If any two things are subsets of each other, they have to be the same, so it's anti-symmetric. And it's transitive. If this is a subset of that, which is a subset of that, then this is a subset of that. So it's transitive. So this is known as a total order. Everything's lined up in the hierarchy, and you know where everything belongs. This is a partial order. There's a hierarchy, but you don't know how to relate A to B to C. No one of them is a subset of the other. They're not necessarily bigger or smaller than each other. So this is a hierarchy chart where everybody's exactly got one spot in the chain. Everybody knows where they are in the pecking order. This is a hierarchy where some people are at the same level and you don't know how to compare them, but there's still an overall order. So these are very important. The same kind of thing happens if you can show that a certain relation is a partial order or a total order. You get all this other mathematical stuff that comes along for the ride because those things hold for every single partial order. I remember working on a paper once as I was looking at PhD stuff, and there was a particular problem that worked for any partial order. And so the question was, will it work for what we wanted to do? All we had to do was establish that our relation was reflexive, antisymmetric, and transitive, and then we knew their relation, their algorithm would work for it. And so that's the kind of thing you'll occasionally run into. All right, this complicated stuff, as I said, it's actually not too bad. There's just lots of definitions. As I said, I don't know yet whether I'm even going to have you do anything with this. If I do, I'll try to give you more documentation or something. But I wanted to show it to you for now because it is an important aspect of discrete math that often isn't covered. It is in our discrete math book, but it wasn't in this book. So I wanted to at least give you a video of it. Thanks.